Our strategy for drawing the Haworth structure depends on if we are dealing with an aldose or a ketose. So we're going to start with how to draw the Haworth structure of an aldose. And I'm going to give you, what you're going to get here is a really super simplified how-to. This is not going to be a very scientific explanation. It's just going to really be kind of a quick and dirty, this is how you're going to take one drawing and turn it into a totally different drawing. So we're going to use a 6-carbon aldose because that's most of what we're dealing with. And my OH groups are going to go left side, right side, left side as we go down the chain, with the end of the chain being a CH2OH. And to help us with this, we're going to number our carbons from top to bottom, 1, 2, 3, 4, 5, 6. This is D-galactose. And that's going to, the name is going to be relevant when we get to the end. So the first thing that I want you to do when you're being asked to draw a Haworth structure is to either literally or in your mind turn the molecule 90 degrees to the clockwise, this way. So we basically want to lay it on its side. That's going to make it easier for us to transition into the cyclic shape. So when we move the molecule and we turn it clockwise, you've got to be really, really careful about how the different OH groups, where they end up when you turn the molecule clockwise. So if we're going to be rotating it like this way, we have to think about where are these things, the things that are on the right side, are they going to be on the top of our drawing or are they going to be on the bottom of our drawing? And sometimes it helps to literally just turn your paper sideways as you're doing this. If we were sitting in class, I would turn my paper sideways 90 degrees to the right to help you visualize exactly how to put this together. As far as this last carbon at the end, it's kind of hard to figure out exactly how to draw him. I'm just going to kind of go sideways like that with it. And let's continue with the numbering so that you can keep track of the carbon atoms as we go through this. 1, 2, 3, 4, 5, 6. And again, I cannot say enough. It's going to be really important that you make sure that you get all of your substituents on carbon 2, 3, 4, 5. Get them going in the right direction when you do this turn. Carbon number 1 and carbon number 6 is not going to matter where things point, but 2, 3, 4, 5, it always matters. So once you get it turned on its side, then you are going to transfer that into the template for an aldose in the Haworth structure. So the template is going to look like this. The template is like the generic kind of version of the cyclic shape. This is what it looks like. And the carbons are, this is carbon number 1, this is carbon number 2, this is carbon number 3, this is 4, and this is 5. I'll tell you where 6 is in a second. It's very, very important that you maintain this exact same template with the oxygen in the same position and 1, 2, 3, 4, 5 in the same spots. Don't make your own thing up here. You always need to use this exact shape. Okay, so don't do your own thing. Don't get creative. This is not the time to get creative. So don't go this way with it. Don't put oxygen in a different place. And don't do different numbers. So like don't start number 1 up here and go around this way. Do it exactly the way that you see right there. If you do it this way every time, you're going to be okay. So first thing that we're going to do is fill in carbons 2, 3, and 4. Carbons 2, 3, and 4. So that on our sideways drawing is these guys. If we look at carbon 2, you can see that he has an OH down and an H sticking up. Carbon 3 has an OH up and an H sticking down, and carbon 4 has an OH up and an H sticking down. So we've got that. Our OH is down, H is down, H is down. So there's that. For carbon number 5, if you remember from that little drawing thing that I did in that mole view software, carbon number 5's OH is actually the one that is looping around and connecting over here. So that little guy is actually disappearing. It's going to be gone completely. And all that carbon 5 is going to have left on it is its hydrogen, which is always going to be pointing down every single time. And carbon number 6 will be up here as a CH2OH hanging out of the ring. So there's our carbon number 6. All that we have left over here on carbon number 1 is the OH that's left over from the formation of the hemiacetal. And the OH can either be sticking up or down, either one. So we have 2 options, which that means that gives us another chance to practice drawing this molecule. So we're going to start with our template. Let's number our carbons, 1, 2, 3, 4, 5, and now we know carbon number 6 is up here. I like to just go around the ring once I've got it drawn and put in all of my straight bonds like this, getting myself emotionally ready to fill this in. So here's carbon number 6. And let's make even more on this template. We know that every time CH2OH is going to be up here and H is going to be down here. Like, this is truly the template of a Haworth structure of an aldose right here. Because your only options when you're drawing these, the only thing that you can vary are these bonds right here. Everything else is exactly the same. So let's fill in. We know that carbon number 2 is OH down, carbon number 3 is OH up, carbon number 4 is OH up. Sometimes I write my OHs backwards when I feel like I'm running out of room. That's all that's going on there. And then carbon number 1, like I said, the OH can either be up or down. When the ring closes and makes this cyclic structure, sometimes the OH group ends up, and sometimes the OH group ends up down. So for any given monosaccharide, it could be up and it could be down. It could be either one. And we have different names or different prefixes for the sugar depending on where the OH group ended up. So for the first one that we drew, where the OH group ended up, this is D-galactose. It's still D-galactose even when it's circled up like that. When the OH group is up, we call it beta D-galactose. And when the OH group is down, we would call it alpha D-galactose. And the way that you can remember alpha versus beta is that alpha looks kind of like a fish. It's got a kind of a fish shape to it. And the fish are down swimming in the sea, whereas beta, which does not look like a bird, but bird starts with a B and beta starts with a B, and they are up high in the sky, much like the OH group is down under the sea with the fish, and the beta is OH up high with the birds. So that's how you can help remember which is which. These 2 different structures of D-galactose, the alpha structure and the beta structure, they are called anomers. Anomers, that's a type of relationship. Anomers are the alpha and beta structures of a cyclic monosaccharide. So you could hear something like, draw the alpha anomer of this molecule, or draw the beta anomer of this particular molecule. In addition to calling these 2 molecules anomers of each other, the carbon that dictates whether it's alpha or beta, carbon number 1, is referred to as the anomeric carbon, because that is the place, the carbon, that is making the decision about whether the molecule will be an alpha or a beta. So we call that the anomeric carbon. In nature, the molecule, D-galactose in this case, is constantly switching back and forth between the alpha and the beta anomer. So it'll be closed up as the alpha anomer, and then it will open itself up to a straight chain and close itself back up again. And when it closes up again, maybe it turns into the beta anomer, and then it opens back up and closes back up again. So it's this constant opening and closing process that we call mutarotation. Mutarotation is just the natural, spontaneous, meaning that we don't have to manipulate it. It does it all on its own. Spontaneous conversion from the alpha anomer to the straight chain monosaccharide to the beta anomer, and on and on and on. Just this constant process.